Okay, now that we have done this quantitative analysis, at least for a first order system, let's introduce a tool that can be applied to any order systems, but since we have this analysis, now we can define it properly. And so the tool that I'm going to talk about is the Bode plot or Bode diagram. So the Bode plot, for this makes sense only for a linear system. So for a linear system, the Bode plot is nothing but a plot that reports in a graphical way the result of our analysis. So the idea is that you have a certain input u of t that is equal to cosine of omega t. Here you have your linear system. Doesn't need to be first order. And here you have your y of t. Your y of t is going to be of the form, is going to be a sinusoid with the same frequency. And this is true, we are going to see this is going to be true for linear systems of any order. If you inject, if the input you inject is as the form of a cosine with a certain frequency omega, the output is going to be a cosine with a certain frequency omega, but it's going to be scaled, its amplitude is going to change, and also its phase is going to be shifted. So this is going to be y times a certain quantity. I'm going to call it g, and I put a modulus here, g times cosine of omega t plus a certain change shift. So this is called amplitude gain. It's actually a gain if this g is larger than 1, your amplitude gets bigger. Otherwise it's called an attenuation, but the general name is it's called gain, amplitude gain in general. And instead this quantity here is called phase shift. So what is the Bode plot? The Bode plot is nothing but, think of it as a thought experiment where you do the following things. You'd like to report this g. This g is a function of omega, so important, it depends on omega, and also the phase shift. If you check the expression that we have written, at least for the first linear order systems, this phase shift depends on omega as well. So it's nothing but reporting omega by omega what is the amplitude gain of your system and what is your phase shift in your system. So the Bode plot is actually two plots. On the x-axis you report omega with one caveat that I'm going to tell you soon, and then there is the second plot where you report your phase shift. So here we report omega, and here you have your g as a function of omega, and here you have your phase shift as a function of omega. So your Bode plot is the Bode plot reports for every omega greater or equal than 0 the corresponding gain g of omega and phase shift. phi of omega. The caveat is that Bode plot uses a logarithmic scale. So the way it's typically represented, if you have, instead of reporting omega in a linear scale, so if it was a linear scale, you have omega equal to 1, then omega equal to 2, omega equal to 3, all equally spaced. Instead, you report omega, and so I'm writing it here. Omega is reported in logarithmic scale, so in log scale. What does that mean? So if here you have omega equal to 1 and here you have omega equal to 10, at the same distance from 1 to 10 on your axis, you'll have here omega equal to 100. So the distance from 1 to 10 is equal to the distance from 10 to 100. That is going to be equal to the distance from 100 to 1000, and so on. So your frequencies are reported with this in this scale, and this is true for both the plot that you have for the gain and for the phase. So this is one thing that you need to remember, and there is another thing that involves only the gain. Also, the gain is reported in not in its standard value, but you report it in decibels. What are decibels? If you want to convert a quantity into decibels, that's what you do. You take 20 times the logarithm of the quantity. So let's be precise, it's going to be 20, but let me put 10 here. So what happens is that you typically plot, you want to plot in decibels this amplitude square, this gain squared. So in order to have something converted into its standard units into decibels, you take the logarithm and multiply by 10. Since it's a convention in the Bode plot that you plot the power of this gain, so the squared of this gain, this 2 actually moves out of the logarithm, and so you get a 20. So the other important thing is that amplitude gain is plot in decibels. So this is how you draw it. And so once you have your gain for every omega, your phi of every omega, and you have your omegas, so long as you do everything correctly and you report in your scale, you have a logarithmic scale for omega, and also you report the decibels for your amplitude gain, you're going to be fine. The reason why this is done is that once upon a time we didn't have computers that were very fast and efficient at drawing plots, and so these plots had to be drawn by hand most of the times, or it was actually a good idea. Often, just to do something quick, you had to draw this by hand. So the reason, I want to write it here, the reason behind the choice of decibels and logarithmic scales and log scale is because using these scales it is easier to draw the Bode plot without using any numerical tool. That's the reason. And now, because it was easier to do that by hand, it's stayed in the tradition. So we do the Bode plot still in the same way. And we are going to see what are these rules, because actually the rules that we use to draw the Bode plot by hand are going to give us some intuition, and it's important in engineering to have some intuition about the system. So even though you're never probably going to draw a Bode plot by hand after this class, in this class you're going to do it, but after this class, even though you're never going to do that, the intuition that you gain behind it is part of the knowledge that an engineer is, an electrical engineer at least, is supposed to have.